Welcome to the chain rule and the fundamental theorem of calculus. So just a quick review of both of those. Recall the fundamental theorem of calculus. Part one said that if lowercase f is continuous, sorry about that, on the closed interval AB, and capital F of x is defined as the definite integral from a to x of f of t dt, then we have that capital F prime of x is simply equal to f of x, lowercase f of x. We also have our chain rule, which said that if we wanted to find the derivative of f composed with g of x, that this is the same thing as taking the derivative of f with respect to the derivative of f and plugging in g of x, then multiplying by the derivative of g evaluated at x. So if we put these together, if we have a capital F of x is equal to the definite integral from a to sorry about that, from a to, I'm going to use u of x of lowercase f of t dt, then this is the same thing as taking the derivative with respect to u of the definite integral from a to u of f of t dt, and then multiplying by the derivative of u with respect to x. Or in other words, that first part is now just f prime evaluated at u of x. Sorry, not f prime, just f, right? Capital F prime evaluated at u is lowercase f evaluated at u of x. And then we multiply it by u prime of x. So for an example, let's consider the function capital F of x is equal to the definite integral from 1 to x squared of 1 over cosine of t plus 2 dt. So cosine of t falls between -1 and 1. So adding on 2, we don't have to worry about a 0 in the denominator. So this piece here is continuous everywhere. And then 1 is my a. And then we would usually have an x up top as our bound of the interval. Right now we have x squared. And so what we're going to do is we're going to go ahead and set x squared as our u. Right? So what we wind up getting then is we are looking at f of x is equal to the definite integral from 1 to u of 1 over cosine of t plus 2 dt. So if we go ahead and take this derivative, again, we have our chain rule. So capital F prime of x is equal to the derivative with respect to u of the definite integral from 1 to u of 1 over cosine of t plus 2 dt. And then we should multiply by the derivative of u with respect to x. So this first piece, that is just fundamental theorem of calculus, part 1. We just plug in u to the inside of our integral. We have 1 over cosine of u plus 2. And then we should multiply by the derivative of x squared with respect to x. So this becomes 1 over cosine of x squared, whole thing plus 2 in the denominator. And then we multiply by 2x. So we wind up getting 2x over cosine of x squared plus 2. Next up, we want to consider the function capital G of x is equal to the definite interval from 3x to 5 of 2t minus 1, the whole thing cubed, dt. So again, our the function inside of our integral is that 2t minus 1 cubed, which is definitely continuous. Our a here is acting as 3x, which we're used to having a constant there. So what we can do is we can go ahead and rewrite this integral with the bounds reversed. So if we reverse the bounds, what happens is that the integral becomes negative. So we are looking at the definite, and the g of x is equal to the negative, the definite interval from 5 to 3x of 2t minus 1 cubed dt. Now this looks like what we were working with before. So we're going to go ahead and set u to be 3x. Again, that just comes from that upper bound that was defined in terms of our variable. And so we have g of x is equal to negative times the definite interval from 5 to u of 2t minus 1 cubed dt. Then when we go ahead and take this derivative, we get that g prime of x is equal to negative the derivative with respect to u of the definite interval from 5 to u of 2t minus 1 cubed dt. And then times du dx. So again, fundamental theorem of calculus says if we differentiate with respect to that upper bound, we just plug in the upper bound. So we have negative 2u minus 1 cubed times, and then u, we're looking at the derivative of 3x. So we have negative, in parentheses, 2 times 3x minus 1, the whole thing cubed, times the derivative of 3x with respect to x is just 3. And simplifying this out, we wind up with negative 3 times 6x minus 1 cubed. Finally, here we have x's in both the lower and upper bound. So what we're going to do is we are going to split this integral at some value. You can use whatever you want. Keep in mind the fact that sine of t, again, is continuous. So we have x in both the lower and upper bound. And so what we're going to do then is we will split the integral. So I will just split it 0. But you could use whatever value you want. So we'll do the definite integral from 2x plus 1 to 0 of sine of t dt. And then we'll add on the definite integral from 0 to x squared minus 3x of sine of t dt. So this was one of our definite integral properties, that we could split our integral by breaking somewhere in within the bounds. And in fact, you don't have to split at a value between the bounds, as long as the function is continuous the whole way. So in this case, then what we can then do is we will go ahead and reverse our bounds of this first one and make it negative. So we'll reverse the bounds and make negative. So we'll have one integral, which is 0 to x squared minus 3x sine of t dt. And then our other integral will now be subtracting the definite integral from 0 to 2x plus 1 of sine of t dt. So what I was writing here, this is this integral here, became negative. At this point, we can have two different functions in our upper bound. So for this first one, we'll go ahead and set u equal to x squared minus 3x. And we'll set v equal to 2x plus 1. So those are just coming from our new bounds. So we are looking at h of x is equal to the definite integral from 0 to u of sine of t dt, and subtracting off the definite integral from 0 to v of sine of t dt. When we go ahead then to take the derivative, we have h prime of x is equal to the derivative with respect to u of the definite integral from 0 to u of sine of t dt. Multiply that by du dx, there's our chain rule. And then from that, we are subtracting the derivative with respect to v of the definite integral from 0 to v sine of t dt. Chain rule, we then multiply by the derivative of v with respect to x. Again, fundamental theorem of calculus, this first derivative with respect to u just becomes sine of u, plug in that bound, and we are multiplying by the derivative with respect to x of u is equal to x squared minus 3x. Then from here, we are subtracting derivative with respect to v, where v is our upper bound. We just plug in that bound. We are subtracting sine of v. Then multiplying by the derivative with respect to x of v was equal to 2x plus 1. So this becomes sine of x squared minus 3x multiplied by 2x minus 3. And then we are subtracting sine of 2x plus 1 times derivative of 2x plus 1 is 2. Just rearranging this slightly. This becomes 2x minus 3 multiplying sine of x squared minus 3x minus 2 times sine of 2x plus 1. In general, what we have just seen. Actually, I'm going to switch colors. 1 moment. So in general, we have seen that if f of x is equal to the definite integral from a to u of x, lowercase f of t dt, then we get that capital F prime of x is simply equal to f of u of x times u prime of x. We saw that if we had capital F of x equal to the definite integral from, let's go from v of x to b, lowercase f of t dt, then that derivative of capital F prime, capital F of x is equal to, we do negative, because it came from the lower bound. Remember, we swapped our bounds. Negative f evaluated at v of x, negative lowercase f evaluated at v of x times v prime of x. And then if we had capital F of x equal to the definite integral from v of x to u of x of lowercase f of t dt, then we have that capital F prime of x is equal to lowercase f evaluated at u of x times u prime of x minus lowercase f evaluated at v of x times v prime of x. Sorry about that. Didn't update that last bit of the line. 1 moment. Okay, so we had capital F prime of x is equal to that lowercase f evaluated at u of x times u prime of x, and then we subtract off lowercase f evaluated at v of x times v prime of x. So that upper bound was the positive component, and the lower bound was the part that we had to subtract off, which is consistent with our fundamental theorem of calculus in general.